comprehending the lectures, probably one or two in vibrations and structures. So I can kind of
yeah, systems is not a hard course, and that's they put systems in place in your curriculum to just make sure you also have fun.
Yeah. We got our final project in that class coming up. I think it's like a 20-page report or something.
Wow.
Less than 20. Yeah, I know. I read that. I was like, oh, that's a lot to write about, like fuel systems. I don't know that much about like simple stuff.
He actually, wow. They assigned that class to me without even telling me. So Ryan, I remember, you know Ryan, right?
I've heard of him. I haven't met him.
Yeah, Ryan came to like the lab class one day and told me that, what are you gonna do for aircraft systems? I was like, I'm not teaching aircraft systems. He said, yes, you are. So I went back and checked, and she said, yeah, yes, I am teaching. So I went there. I mean, I'm not an aircraft systems guy, right? I designed the class. I worked the syllabus. I found the textbook. I was reading the textbook to learn and then teach it. Then, fortunately, they hired Vouch. He is a systems guy. So, but he follows my syllabus. So all of the quizzes you have, all of the projects you have is essentially.
It's not really that hard of a class. I can kind of like just not even like take notes and just watch the lectures, and then whenever the quizzes come, I can just look through the slides and answer the quizzes. It's not that bad.
Yeah.
Vibrations is getting a little hairy though, with the eigenvalues and 2 degrees of freedom.
Yep. Vibration can be very hard. That's true. Let me just write down this equation. We have these long equations in orbital mechanics. I really don't know what to do with those. That's very.
So is our next exam final? Is it comprehensive or is it just orbital?
Just orbital. I'm actually from next semester. Probably what I'm going to do is just to have 3 exams and do just sections for all 3 exams. So not a real final, just part, because I think that's going to be easier.
That's what my calculus did in high school. We had like a first semester exam and we had a second semester exam. They were like separate. So why would I test you on something we haven't talked about in like limits back in September when we're doing integrals now? Like you know what a limit is. So like what's the point?
Yeah, if you don't, then you can't do integrals properly as well. So yeah, that's what we did in my country for all of the classes. But here, for whatever reason, I think, yeah, I think it's going to be easier for students and me. Let me just write these equations on board.
The last full lecture I was in here was the 23rd. That was like 2 Tuesdays ago.
Wow. I'm happy to see you are up and running again.
Oh yeah.
That's.
My roommate called me during vibrations 2 Tuesdays ago and said, "Hey, you need to come home because we have COVID. You probably have." So I had to get up in the middle of Austin's class and leave.
So you are probably a super spreader then.
I hope not. That'd be awkward.
I mean, I've been wearing masks, so that shouldn't be a. But you were not one of those asymptomatic ones.
No, I was feeling a little under the weather that day that I had to go home, but I was hoping it was just allergies.
Yeah, that's. Hopefully this will go away. I'm just tired of wearing a mask, honestly, everywhere. And people don't wear their masks anymore. So.
The next fall is supposed to be quote unquote back to normal class-wise.
Yeah.
That's a long one.
It is a long one, yeah.
Are we gonna have like the simplest form for the use of it?
No, we're not gonna use this at all. Okay. That's. But we have to have it on board anyways. A plus B. I wanted to assign a homework to you guys to go out. No, assign another homework, like an assignment, to ask you to derive these integrals.
Like a bonus or?
No, as a homework. But then I went in and I saw that it is. I don't remember how to find the solution to this myself, so it is gonna be. It is gonna be very hard for you guys to do this. So I just decided against it.
I talked with Austin a little bit last Friday about whether to do grad school or just go into industry.
Okay.
As like an entry-level aerospace engineer working at, say, like Boeing, Lockheed, Northrop, wherever, what is some of the things that you have to do?
I honestly can't answer that question very. I can't say I know exactly what you're gonna do, but in general, as someone with an undergrad, let me put this. Let me finish writing this, then. First, two points. First thing is you probably want to talk to someone like Yi Wang, who teaches flight dynamics and control, right? He has worked as a manager in CFD core, right? Me and Austin, we are all academia, came straight out of academia, right? But based on what I know, based on what I've seen, you probably end up doing a CAD design or whatever. It really depends on where you end up, right? You can end up in QA, right? Or QC, right? Those things is a whole different ballpark. You probably need a whole like internship to learn whatever you need to do, because we don't really teach QA and QC in this. I mean, you do learn some in LOTS class, but not anywhere else. But if you end up as an aerospace engineer who is tasked with designing aerospace things, you will only do CAD analysis, aerodynamics analysis using ANSYS, Fluent, all of those softwares, right? Nothing more. So you won't end up in an R&D part of a company, any company. You need to have a master's or a doctorate. Okay?
Doing my best to avoid anything related to coding. I'm not good at coding. Like specific script writing and stuff like I'm okay with CAD and like using the CAD function for like the heat transfer analysis and stuff like that, but I'm not a big fan of coding. I know I feel like if I went through the process of learning it, I'd be fine.
Yeah, I'm pretty sure.
I don't struggle that much when it comes to coding, like when it comes to vibration. Yeah, vibration. I don't struggle that much, but like it's a little confusing sometimes.
So in the industry, you will, unless you work in a company like ANSYS or SolidWorks, where you are tasked with like writing an application, right, that is going to be used by other engineers, you won't need to do any coding. So that's your question then. Are you going to do any coding, right? Okay. So let me put this: if you start working at Boeing, you are going to use either Creo, SolidWorks, higher level analysis, ANSYS, Abacus, all of those softwares.
I can manage that.
Okay.
I can deal with that.
But that's a huge but, right? You have to learn programming as an engineer because everything is moving towards data science and big data, right? Nobody really does a mathematical analysis like using ANSYS. So I assume all of any industry will move towards that part. So you have to learn Python a little bit. I'm thinking of doing a little bit of Python. What software do you use for vibration? MATLAB? Yeah.
Python's free, and he suggests learning it.
Yeah, it's not a bad one to learn.
I think he teaches a summer course in Python.
Yeah, machine learning. Not just Python, it's machine learning. Yeah, I don't know if you guys can take it because you don't really have an elective.
It's a 500 level course.
Yeah, but your electives are like 2 out of these 5 courses, right? So
Yeah,
you're.
I think we can still choose to take it, especially since we've had Austin. So he might be able to give us
any class you want.
Huh?
Pay for it.
Yeah.
You can choose to have any
Well, let's
class
take
you
it.
want.
That's correct. Okay. So Trey and Lawson are here. You will get bonus point. Let's see who is online.
Have there been attendance issues?
No, but people coming late, so I just decided to give whoever's here early. Steven and Igor, let me write it down. Do you have a pen? Yes. Just so I remember. Trey left though. Okay, bonus. Today's bonus goes to Igor, Steven, Emery is here as well, and Trey, everyone, right? Except Nirlab and Nicholas. Who else? Lawson. Okay. There hasn't been any attendance issues, but I received a comment from received a comment from faculty that why aren't you enforcing attendance policy? I said, okay, I'm gonna do it. Well, I think attendance policy, enforcing attendance is a little, in general, is not a very good idea. And
Do they not know about the online?
no, so you guys usually come in late, like 5-10 minutes late. I don't really care. You are paying for this, so if you come in late, huh? Coming late or?
Coming that late.
I don't know what to say. It's just I don't. Let me put it this way. I'm not here to teach you how to be polite. So, and I don't really. Well, I heard a comment, so I'm just trying to be more respectful of authority, of my higher authority. Okay, so let's start chapter 3. Okay, in chapter 1, we had a little bit of chapter 1 of the orbital mechanics part. We had a little bit of dynamics of point masses. It was essentially a review of the previous chapters of your dynamics course that you should have seen all of the things that we discussed in chapter 1 in your dynamics course. And then we moved to the meat of the orbital mechanics, the Orbit's equation, the Kepler's laws, different Kepler's laws. We talked about circular orbit. We talked about different elliptical orbit, hyperbolic and parabolic trajectories. We talked about the Jacobi constant, the escape velocities, and all of those fun parameters, right? Today, we are going to talk about orbital position as a function of time. This essentially means that we want to find how long does it take for a satellite in an elliptical orbit to go from the apsis line or the periapsis to a specific true anomaly, theta, right? How long does it take for that to happen? Or the other way around. After this many hours, what is the true anomaly? What was the true anomaly? Theta, right? That was the angle. So this is all of the things that we want to discuss in this chapter, and we are going to do the analysis for circular orbits, all of the elliptical, and all of the other trajectories, and then we will talk about universal variables, and we'll be done with chapter. My plan is to finish chapter 3 today, right? Start and finish it today because it's a very short chapter. So how can we relate true anomaly to time? We had this one equation for angular momentum. Angular momentum is equals to r squared, your position vector, multiplied by changes of theta to anomaly with respect to time. We already know that this theta dot is d theta dt. So we have already found the starting point, right? We have something that relates theta to time. Let's rearrange this. Let's move dt to the other side. So you're going to have h divided by r2 dt. Or let's actually do this. dt is equals to r squared divided by h d theta. Okay. We already know that angular momentum is a constant value in any orbit that we are dealing with. But r is changing. Do we know how r changes with theta? What is the relationship between r and theta? Is it something we already have knowledge of? Anyone? Okay, we have a couple of comments here that I haven't seen. Yeah, that's discussion has passed. How can we relate your position vector to theta? Because if you want to find the time pass from pre-apsis, we have to take the integral here, right? If you want to take the integral, we have to know the dependence of r on theta. H is constant, right? We don't care about it, but we have to find the dependence of r on theta. What was the orbit equation? What was the main orbit equation we dealt with?
H squared over mu times 1 over 1 plus e cosine theta.
That's it. So we have found the solution, right? R is related to theta. If you plug that in and move things around a little bit, this is what you are going to get. Mu squared over h cubed dt equals to dt divided by 1 plus e cosine of theta squared. We have moved the constants to the time side, the left side, and we have moved the cosine. I mean, we couldn't move it. We didn't move it. We just left it there. So one thing that you have to note here is that we are going to assume that time at pre-apsis is 0, right? The origin of time is an arbitrary value. So we are going to assume that at pre-apsis we are at time 0, and then we're going to calculate time. So if you take the integral from Tp to T, mu squared h cubed dt is equals to the integral of the true anomaly at the pre-apsis is 0, right, to theta 1 plus cosine of theta e cosine of theta squared. And we agreed to set the time at pre-apsis to 0.
Okay. Can we take the integral on the left-hand side? Mu and h are constant. We can take them out of the integral. So it's essentially just the integral of dt, which means that you're going to end up with t. So let me actually, mu squared divided by h cubed t. What about this other side? Can we take the integral of the other side? Is it easy? I mean, we definitely can, but it is not easy to do so. It is a very hard integral to take. I was actually telling Lawson that I wanted to assign taking this integral to you as an assignment. Right? We have different conditions, but just the solution is written here on this side of the wedge. It is just the final solution, right? The derivation would have been a project, right? But then I decided against that. Probably next semester, next year. So, yeah, probably next year. Yeah, OK. So we have to take this integral. If we can take this integral on the right-hand side, we have the solution, right? But the idea here is that taking this integral is going to be a very hard task to do. And also, the solution to this integral is going to change based on the value of eccentricity. Right? Look at this. This is the general form of this integral. For us, a is always 1, right? And b is always your eccentricity. So in these solutions, wherever you see a, you have to put in 1. Wherever you see b, you have to put in eccentricity, OK? So this first one is the solution for the case b is smaller than a. What does it mean? Eccentricity is smaller than 1, right? What type of an orbit or a trajectory is this? If you didn't remember this, you always start with at the eccentricity of 0, right? What is the eccentricity of 0? A circular orbit, right? So what happens if you increase the eccentricity a little bit, but you stay below 1? Elliptical. So this is a solution for elliptical orbit, right? This one tells us eccentricity is equal to 1. What kind of a trajectory is this? Parabolic, right? And this one, the third one, is for the case where eccentricity is larger than 1. So we are dealing with a hyperbolic trajectory. OK? So we can take this integral, but it's going to be a little complicated. As you see, we don't really have any solution for the circular orbit, where eccentricity is 0. Why is that the case? I mean, we already have that, right? We already plugged that in. What will happen to this when you plug in eccentricity 0? Just 1, right? So it is just an integral of dt. So that's the circular is actually the simplest case. We didn't need to put it there. So let's start the analysis and come up with a solution method for the orbital position as a function of time for a circular orbit where eccentricity is 0. Of course, we are not going to use these long equations because that doesn't make any sense, right? So we're going to simplify them. But eccentricity 0 or circular orbit is already a simplified case by itself. your relationship between time and true anomaly is going to be h cubed divided by mu squared theta. On the other side, we only have the integral of the theta, which is theta, right? We can actually write this as a function of orbital position. The orbit equation for a circular orbit is, since eccentricity is 0, all of these parts are going to be equals to 1, right? So this will be your orbit equation. You can plug that in and get time as a function of your position vector. That's r to the power 3/2 over a square root of mu squared theta. That's how it is written in your book. So we're going to follow whatever you have in your book. And your period in a circular orbit, this is something we have also seen before. That's 2 pi r cubed okay? Which means we can write these equations as a function of period. You can rewrite the equation 2p divided by t. This is, it doesn't have to have a square. It is not raised to the power 2. Okay, so very simple. Circular orbit, you can find the true anomaly as a function of time. Again, in these type of problems, you will be asked to find the true anomaly after some time has passed, right? Or the other way around, to find the time that it takes for your satellite to get to that specific true anomaly, okay?
So we'd be given a capital T and a lowercase t and then find theta.
You definitely won't be given a capital, not definitely, but you probably won't be given a capital T.
But we'd be given, in that case, I guess, an R and mu.
Just a mu. Maybe an angular momentum.
Okay, so
Right. Yeah, because well, we will solve a lot of examples, hopefully, when we are done with the last chapter, which is going to be the interplanetary flight. Then we will dedicate all of the other lectures to solving examples, okay? Because this is something, we haven't solved that many examples for this part of the class. Okay, so let's move on to a little more complicated part of this chapter, elliptical orbits. So for an elliptical orbit, your main equation is going to be equals to, this was the main equation we had for all of them, right? Mu squared divided by h cubed t is going to be equal to the integral of d theta divided by 1e cosine of theta. This is the general equation, right? And we already have the solution. This is the first solution for the elliptical orbits, right? You already have one solution. So this part, this left-hand side of the equation is going to be equal to this, where all of the x's are theta, x also is equal to theta. All of the b's are eccentricity, and all of the a's are 1. This is going to be your general equation, right? But what we're going to do to make things a little simpler is that we are going to introduce a new variable called the mean anomaly of elliptical orbit. ME. And this ME is going to be equal to the solution to this integral. Okay? Let me write a simplified form of the integral for you, but that I just want to make sure that you are exposed to this part. If you simplify this, this is what you essentially, not this, actually. So ME is equals to 2 tangent negative inverse tangent of a square root of 1 minus E, 1 plus E, tangent theta over 2 minus E 1 minus E squared. And that's ME. Only this is only true for an elliptical orbit. And this, so this simplification is actually, this is, I think I said it wrong. This is a part of this solution, not all of it. Okay. So what does it mean for this equation for an elliptical orbit? This equation is going to become mu squared divided by h cubed t. That is going to be equals to 1 minus E squared 3 by 2 ME. So this will be your final equation that will give you the orbital position, orbital, the true anomaly as a function of time. Okay, you can play with this a little bit. You can find the mean anomaly for an elliptical orbit as this mu squared 1 minus E squared divided by h cubed t. Okay. Okay. So what do we have right now? We have an equation that is going to give us time as a function of mean anomaly. Can we make this a little simpler? Yes. If you go back to your notes, you're going to see that this part of the equation is actually related to your period. The period of the elliptical orbit is actually equals to 2 pi divided by that period. So your mean anomaly is going to be equals to 2 pi divided by your period multiplied by time. If you compare this equation with the equation we had for circular orbit, you're going to see that this is essentially very similar to that equation. This means that your mean anomaly is basically acting as the equivalent circular true anomaly in an elliptical orbit. Okay? Just to, it was a very complicated name for a variable that is there for simplification, right? So are we clear what happened here? The only thing we did, we just removed the complex part of the solutions, right?
So they still mathematically handled the same? Because that's the same thing we had for theta.
We don't have the theta.
It's the circular.
But we are in an elliptical orbit. So we are going to think of something, right? We cannot just finding the mean anomaly is not going to be very helpful to us. Okay. There are a couple of variables that we need to become familiar with. One is the called the mean motion. Let me read. Mean motion, and this mean motion is the average angular velocity. We can put it this way, right? N. Because the angular velocity here is not constant, so we come up with an average angular velocity called N, called mean motion. This essentially means that if you have this mean motion, you can find the mean anomaly multiplied by your time. Okay. So to have an easier, we already have a relationship between theta and mean anomaly, right? Through this complex here, through this complex equation, right? But we don't want to use this, right? That's the idea. We want to come up with an easier set of equations that is going to help us. So to do so, I'm just going to wipe this part because we have already seen this, right? So to do so, we are going to introduce a new parameter called the eccentric anomaly, E. Eccentric anomaly. E. What is this? This eccentric anomaly, let's say this is your elliptical orbit. Not a very good ellipse, but just accept it from me. Okay, this is the center of ellipse. This is your focus. This is your empty focus. Okay. Then let's try to draw a circle around this ellipse, right? The theta in this position can be defined as this, right? If you continue this line to get to the location on the circle that surrounds your ellipse and find the angle here, this will be the eccentric anomaly.
It's not the center.
It is the center for the eccentric anomaly.
The point to the right that has the angle on it.
Oh, that's how you were not here. Let me actually refresh everyone's memory, right? For an elliptical orbit, we have two foci. How do you pronounce that, right? True anomaly is this angle, okay? For an elliptical orbit. For a circular orbit, the two foci are essentially on top of each other, right? You have one focus point, which is the same as the center of your circle. Okay. From the previous classes, you probably remember that this length is A multiplied by your eccentricity, okay? And this is R cosine of theta, okay? So the projection of this on your semi-major axis, which is this axis, right, semi-major axis, is going to be E cosine of theta, right? I'm sorry, A cosine of E. A cosine of E plus or equals to AE plus R cosine of theta. This is the relationship we can find. This is small e eccentricity. This is the mathematical relationship we can find with between E, that's the eccentric anomaly, and theta, the true anomaly. Okay, which is very simple. We are saying this length, which is a cosine of E, right? Let's just make sure that we understand where this relationship comes from. Do you see this color? Is it easy to see? A cosine, a small. Let me redo this. Let me use a different color because I think online people will see this color very well. Okay, elliptical orbit. Okay, center, focus, F prime. This was called the semi-major axis. We also had the semi-minor axis. The idea was that we are going to find a circle that surrounds your ellipse, right? And has the same preapsis and apoapsis, right? Is at the same location as your ellipse. How did we calculate the true anomaly? That's theta, right? What is this length? This is r cosine of theta, right? Projection of r on the semi-major axis, right? Okay. Then we define this angle as E. What is this length? It is this radius cosine of capital E, right? Eccentric anomaly, right? What is this radius? Is essentially the length of the semi-major axis, right? This length. So it's going to be A cosine of E. That is capital E. And here we already have seen that this length is A semi-major axis length multiplied by your eccentricity. This is something you have seen in the previous lectures. We actually have, I think we proved it. It's not that hard to prove. No? Okay, so this relationship becomes true. A cosine of E is AE, A multiplied by eccentricity plus R cosine of theta. And we can replace R with the orbit equation, or with a different form of orbit equation that includes the semi-major axis. If you recall, we had many types of orbit equation when it came to elliptical orbits. So A cosine of E is going to be equals to AE plus A multiplied by 1 minus E squared plus divided by 1E cosine of theta. This is your orbit equation for an elliptical orbit multiplied by cosine of theta. So what do we have here? We have a relationship between eccentric anomaly and theta. Okay. We also have a relationship between mean anomaly and time. So if we can find the relationship between mean anomaly and eccentric anomaly, we have the solution, right? We have related true anomaly to time. That's always the goal here, relating true anomaly to time. But before moving to that relationship, let me actually give you a different form of this relationship. You can just play with this to make it, I guess, easier. We can actually change the relationship between eccentric anomaly and the true anomaly to look like this. You can have tangent of E over 2 is equals to square root of 1 minus eccentricity, 1 plus eccentricity, tangent of theta over 2. So as long as you have eccentricity or either theta or the E, you should be able to find another one. We can rearrange whatever we have here to find the E directly. So it's going to be 2 tangent inverse of the same thing. Okay. So these three equations are essentially different forms of the same equation, right? You probably want to use either of these two because we have removed one variable from it, right? We have removed A from it. You don't need to have A, right? Okay? So again, we have the relationship between eccentric anomaly and theta. We have the relationship between mean anomaly and T. We have to relate the mean anomaly and eccentric anomaly to have the solution. You could have said that this is becoming a little more, you can say that this is becoming a little more complicated than just solving that integral, right? But the problem is that integral doesn't have a closed form solution, right? So the complexity is not the reason we are doing this. It's because we don't have a closed form solution. So we have to come up with a method that we can find the final solution through trial and error, like iterations. And this is what we're going to do. OK, so I'm not going to go over through the proof of this equation. I'm just going to give you the equation. This equation is called the Kepler's equation for an elliptical orbit. Kepler's equation for an elliptical orbit that relates your mean anomaly to eccentric anomaly. E minus E sine of E. Okay? Okay, so let's say you have theta here. That's your link, right? You have three main equations. One, that's another form of the same equation. One, let's call it 1 prime. Then let's call all of these 2's 2 prime, 2 double prime, and this equation 3. Right? You probably need to find eccentricity from other equations you have learned before, but when it comes to relating time to theta, these three equations or the different variations will do the job. Okay, let's say we have theta and we want to find time. So you are told that this is a true anomaly. How long does it take to go from the pre-apsis to that true anomaly? Okay. So you plug it in here, theta, right? You find the eccentric anomaly. And then what you do is you plug it in here. You have eccentricity. Let's say you have already calculated it. You find the mean anomaly. Then you plug it in here. Or here, you find the time. That's your solution, right? But what will happen if you have time and you want to find theta? Okay. You plug time here. You find the mean anomaly. And then you plug mean anomaly here. You find eccentric anomaly. And then you find theta from the equation. But that here, we have a problem, right? Why do we have a problem? This is, let's say, eccentric anomaly is 1, whatever. 1 minus E sine of 1. Okay, I'm sorry. Let's say mean anomaly is 1. 1 is equals to E minus E sine of E, right? Eccentricity 0.2, right? E minus 0.2 sine of E. Does this have one solution? No, It has many different solutions, right? It doesn't, let me put it this way, it doesn't have a closed form solution. It has one solution, but we cannot find a solution using this equation. What should we do now? We should go through a trial and error method, okay? And this method is something you have learned in your numerical methods course. But we are going to go over it, so no worries. It's called the Newton's method, right? Have you heard about the Newton's method, right? Definitely have heard the Newton's method. Newton's method. Again, you only need to use the Newton's method if you are given time and you are asked to find theta. If it's the other way around, you don't need to do this. It's going to be much simpler. Okay, what do we do when we are dealing with Newton's method? We define a function, let's call it f of e, right? We are going to move me to the other side. It's going to be e minus e sine of e minus me. We are looking to find the roots of this function. So essentially, we are looking to find this, right? Which is going to yield this equation, right? What should we do? Take the derivative. That's the first step. You want to take the derivative of this function first. So again, this is f of e. What is f prime of e? What is f prime of e? That's 1 f prime of e. F prime of e itself is 1 minus, we have to take the derivative of sine, cosine of theta, cosine of e, and the derivative of me with respect to e is 0. So you have f of e and the derivative of e. Your next step is to guess a value for e. That's the first starting point. It can be any guesses, but if you can come up with an educated guess, the number of trials and errors is going to be smaller, right? You guess a value. Let's call that value E1. You guess a value. Based on that value, you find the f E1 and f prime of E1, right? And you also find the ratio between the two. Okay? Keep in mind that in this form, we already have one value, one number for ME and eccentricity, right? So you find an FE and FE prime. You take the ratio. If this ratio is smaller than the error that you are given, let's say 10 to the power negative 6, then your guess is an acceptable guess. You don't need to go through any other trial, right? But if it's not, then you calculate the value of E2 using E1 minus this ratio, f of E1 divided by f prime of E1, right? And then this value has to be smaller than your error. If it wasn't, you find the third value using E2 minus the new ratio.
Wait, so if E1 is f of E1 over f prime of E1, wouldn't that give you 0?
What's that?
So if you use, wait, I think I'm a little is that arrow connecting E1 and then F of E1 over F prime of E1?
No. So for E1,
Yeah.
you calculate this ratio. There is no relationship between.
Okay.
For, let me write it down. For E1, do this. Okay? And it has to be smaller than the error. You find the ratio of F divided by F prime, right? If it is smaller than your error, then you have found your value. Do we remember this methodology? You don't need to remember it completely. As long as you have heard about it, you should be fine. We will solve an example. OK, so let's continue the discussion. Let's finish the material. If we had enough time, we'll come back and solve an example. If not, we will solve an example of this whenever we are done with the interplanetary flight. OK? OK, so the next case, we already have the equation for the elliptical trajectory. The next case is where your E eccentricity, that's a small e, is equals to 1, right? Which was this case. Right? So this is a little simpler. This whole equation is a little simpler than is a little simpler than the other cases. Let's go back to the original equation we had. We want to find this integral, mu squared h cubed, integral of 0 to t. We have already done the integral. T is equals to the integral of 0 to theta, d theta divided by 1 plus e cosine of theta, right, squared. OK? This is the original equation. The idea here is if e is equals to 1, this will be the integral we want to find. You already have the solution to this integral. Right? That's it. So we can say mu squared divided by h cubed is equals to 1/2 tangent theta over 2 plus 1/6 tangent cubed theta over 2. And this right-hand side of equation, we are going to call m of p. This is the mean anomaly. M is always the mean anomaly, but this time it is mean anomaly of the parabolic trajectory. OK? Mean anomaly of the parabolic trajectory. OK? Yes. I'm sorry, that is my mistake. Thank you for mentioning it. So this essentially means that MP is equals to mu squared divided by h cubed t. Okay. And to make things a little simpler, they have come up with this another form of the equation. They have introduced a z parameter. Tangent of theta over 2 is going to be equal to z minus 1z, right? And then using the z parameter, we can calculate m of p. Z itself is going to be equals to 3np plus a square root of 1 plus 3np squared to the power 1/3. So this is what you're going to do. Let's say you are given time. You plug it in here, right? You find an MP. Then you plug MP here, you find the Z. You plug your Z here, you find your theta, right? You can actually go the other way as well, right? So for E equals to 1, we have a simpler case. It should be I get a couple of comments. I don't know if there's a random comments on Blackboard. Not the best. Is that the question or? Let's see what about color. Okay, red color. Okay, yeah. Yeah, that's the problem of having a hybrid class. You cannot attend it. What about this green color? Is this good or? Okay, okay. So we have already talked about the circular orbit. We have talked about the elliptical orbit. We have talked about the parabolic orbit. The last thing that remains is going to be the hyperbolic orbit, right? Which one is the hyperbolic orbit? This beautiful equation. Okay. Let's go back to the main equation again. Main equation that we had for finding the orbital position as a function of time.
So that was it for the parabolic?
That's it. It's pretty simple, right? Because we could relate the theta to time very easily. It wasn't that complicated like these two other cases. Okay, and this goes from 0 to x. We have this equation where E is larger than 1. Right? So the solution to your equation is going to be this very beautiful equation. Okay. I guess you can guess that we are going to simplify this, right? Because we cannot solve this. So we are going to define a mean anomaly for a hyperbolic trajectory, m of h, as E square root of E squared minus 1 sine of theta divided by 1 plus E cosine of theta minus natural log of square root of E plus 1 divided by E minus 1 is actually minus square root of E minus 1 tangent of theta over 2. This is plus square root of E minus 1 tangent of theta over 2. So we define the mean anomaly of the hyperbolic trajectory as this. So if you do this, your whole equation simplifies to a much simpler version of things. Okay? You can find the relationship between the mean anomaly of a hyperbolic trajectory and time. That's mu squared divided by h cubed, E squared minus 1 to the power 3 by 2 t. So we have one relationship between time and the mean anomaly, right? And again, the same idea. You don't want to go through this huge mess of a relationship, right? So we have to introduce new parameters. This time, we are going to define a new parameter called f. F is defined as the hyperbolic, is the hyperbolic eccentric anomaly. Since we are dealing with a hyperbolic trajectory, I'm pretty sure you can guess that we have to deal with the hyperbolic sine and cosine. Hyperbolic sine of this f is y divided by b. But what are y and b? Who remembers what b was? We had a and b, right? A was the semi-major axis. B was the semi-minor axis. That is true for both hyperbolic trajectory and a elliptical orbit. So hyperbolic trajectory, we have this pre-apsis, we have the focus, right? Your trajectory is going to look like this. That is the idea. This length was your semi-minor axis, right? That's the distance between P and point N, right? This was your hyperbolic semi-minor axis. Let's say we are at this focus, at this location, at this theta, at this true anomaly. This distance is going to be called y. So we define the hyperbolic eccentric anomaly like this. It's going you're going to take the ratio between this projection, right, and the semi-minor axis. That will be equal to the hyperbolic sine of f. Do we remember hyperbolic sines and hyperbolic cosines, hyperbolic relationships in general? Do we remember those?
I've seen them before.
Have you seen them before? Not that remember.
I've seen them on Kepler.
Okay. So you haven't seen them in any of your mathematics courses?
No.
Seriously?
Yeah. I know it exists, and I know it's different than normal sine and trigonometric functions, but like I'm not totally sure how it's different.
Oh, wow. Okay. So how is that even possible? You don't really need to know them as long as you can know how to calculate them on a calculator, but we will talk about hyperbolic sine and cosine for like 10 minutes in the next lecture, okay? Just to make sure you know, right? Because this is something as an aerospace engineer you should be exposed to, right? You should have seen, right? Okay? Yeah, we will talk about them a little bit. Okay, but just accept this from me. This is we have the f, and again, we have a relationship between m of h and t, right? We are going to use this f, right? We want to find the relationship between f and theta, right? And then we are going to use that f to do the same thing we did with an elliptical orbit, right? Do the Newton's method, right, to find the roots of a function, all of those fun things. Okay. Let's see where we are right now. Okay. So the first relationship we have. Second one is, of course, going to be the relationship between f and theta. So here you're going to have essentially the same relationship, but on the f side, you're going to get hyperbolic tangent of f over 2 is going to be equal to a square root of e minus 1, e plus 1. And then on this side, we have tangent of theta over 2. This is going to be your equation 2, right? And we can rephrase this equation to give us the tangent. Just rearrange this equation to find tangent of theta 2 as a function of this hyperbolic function. And at this point, just accept this from me, that this is what happens if you, it's pretty simple to figure out. So we'll talk about hyperbolic tangent, though, in the next lecture. So this will be your second equation. So we have, what have we done? We have found a relationship between time and the mean anomaly of a hyperbolic trajectory. What else we have done? We have found the relationship between the hyperbolic eccentric anomaly, the equivalent to E in the elliptical orbit, and theta, right? The only thing that remains is the relationship between F and M of H, right? How do you think that relationship will look like? M of E for an elliptical orbit was E minus E sine of theta. Since we are dealing with hyperbolic sines and cosines, and we are dealing with F, we should have the presence of hyperbolic sines and cosines. So your third relationship is going to be this. M of S, H is going to be hyperbolic sine of F minus F. So for the hyperbolic trajectory, you have these three equations that are going to relate time to the true anomaly. Okay. In order to solve this problem, if you were given the true anomaly and you were asked to find time, it's pretty simple. Use this equation, true anomaly, you find F, then you plug F here, you find M of H, and you find time, right? But if it was the other way around, you were given a time and you were asked to find theta, then we have the same problem we had over here. Okay? So we have to use the Newton's method again. What would be the Newton's method here? Exactly the same thing. It's just the parameters are different. So you move M of H to the other side. You define a function of F as hyperbolic sine of F minus M of H. F prime of F here. I'm guessing you don't know that's E. I forgot an eccentricity here. I'm sorry. That's eccentricity multiplied by sine of H. The derivative of a hyperbolic sine is the same as the regular sine. It's the hyperbolic cosine. So you're going to get hyperbolic cosine of F minus 1. This is your F prime and F. Again, you get an F1 based on that. For your guess, do calculate the ratio of F of the function, this function of F divided by F prime of F. If it is smaller than your error, residual, whatever you want to call it, then this F1 is an acceptable value. If not, you calculate an F2 you calculate an F2 CVS pharmacy for where was it? F1 minus using this equation. I'm sorry, guys. F prime of F. And then if this F2 was smaller than the error, then you have an acceptable solution. If not, if it was larger than the error, you have to calculate an F3 using F2, F of, this is F of F1. F prime of F2. Does this make sense? Okay. I guess we have enough time for an example. For a very quick example, though. Let's solve your book example. That's example. Let's see. Where are we? 18. (3.1, 3.2). Okay, we want to find, we are told that a geocentric elliptical orbit has a perigee radius of 9. I want to do it as quickly as possible to make sure we have finished this. We are going to finish. Okay, a geocentric elliptical orbit has a perigee radius of 9,600. So let's call it, what do you want to call it? Let's call it R of P, 9,600 kilometers, and apogee radius of apogee. How do you pronounce this word? Apogee? Apogee. Apogee radius, that's very hard for me. Apogee. Radius of 21,000 kilometers. Okay? And we are given a figure. You want to calculate the true anomaly at 3 hours after perigee passage. So your time is 3 hours. Your t is 3 hours. After perigee passage happens at time 0. So your t is 3 hours. Okay. So what should we do? These are the only things that are given to us. The first thing you want to do always is to see if you can find the angular momentum, if you can find the eccentricity, and all of the other parameters. So can we find the eccentricity? If you go back to let me tell you this. We have millions of equations, not literally, but a lot of equations, right? In this course, you just have to make sure you have all of them written down in your equation sheet, right? Because you probably are going to need, right, all of them. You can derive all of those equations during an exam. That's very easy to derive, right? It's not like partial differential equations. Just have to change the shape, move some parts to the other side of the equation and get a new equation. But I guess during exam time, we don't have the time to do that. So using an RA and RP, we actually already have an equation that is going to help us find eccentricity. That's RA minus RP divided by RA plus RP. So you plug in the numbers we are given. You find this, 0.3, 0.37, 255 as an eccentricity. Your eccentricity that you have calculated is smaller than 1, and you are already told that this is an elliptical orbit. So you're probably calculating the correct value for eccentricity. The next question is, how can we calculate angular momentum? How can we calculate angular momentum? Let's think about this. Let's see if you have an answer for this. What do we have? We have RP, and we also have eccentricity, or RA and eccentricity. We have 3 values, right? That you don't need to go back to your notes. I'm pretty sure this equation you remember. What is the main orbital equation? R is equals to h squared divided by mu, right? 1 plus e cosine of theta. What is the value of theta at perigee? 0, right? So RP is going to be equal to h squared divided by mu 1 plus 1e, right? We have the eccentricity. Mu of Earth is usually given to you. If not, if it's not given, it's 398,600. Okay. We have RP, theta is 0. We have everything. We can find the angular momentum. So your angular momentum is going to be equal to 72,472 kilometers squared per second. That's the angular moment. Okay. So can we find the period? What was the equation for the period of an elliptical orbit? We actually just mentioned that equation. It's this. You don't need to go back. I'm going to give you the equation. 2 pi divided by mu squared. We actually have different forms of this equation as well. This is the form I'm going to use for this example. Cubed. We have all the parameters. We have h, we have eccentricity, we have mu. So your period is going to be equal to, you just plug all of the values in, is going to be equal to 18,834 seconds. Okay? So we have the eccentricity, we have the angular momentum, we have the E, and then what was the next step here? The idea was, if you are given time, which we are given, right? What do you want to calculate first? ME, right? Do we have the parameters for ME? Yes, we just calculated the period. So we are going to use this equation to find ME, right? You just plug in period, you just plug in the time. You just have to make sure that you are consistent with the units, right? If units of period is seconds, your unit of time has to be second as well, and the other way around, right? So if you convert all of those parameters, your ME is going to be equal to, right here, is going to be equal to, and keep in mind that this is mean anomaly. So its units are, it is a dimensionless, but in radians. Radians are not dimension. It's not a dimension. 3.6029 radians. Okay, so we have ME. What is the next step? The next step is to find it in, no, the next step, not the theta. You're escaping the most important step here. Go ahead. So we have this equation that relates ME to E, right? You plug in ME, you plug in the eccentricity. I'm just going to plug in 3.6 for ME for the sake of simplification, simplicity, and 0.37 for eccentricity. This will be the equation. So it is not possible to solve this analytically. So we are going to use the Newton's method to find the roots. We are going to form this function. F of E is equals to E minus 0.37 sine of E minus 3.6. What is the F prime of E here? F prime of E is exactly 0.37 cosine of E. Okay. So we have to guess a value for E. The first code, this is how you need to think about this when you're thinking of E. How many seconds are this t? A small t. 10,800. It's a little more than half of this, right? So we probably have passed the apoapsis, right? That should be very close. So for your E, the simplest thing that you can think of is to choose an E that is close to, let's say, 180 plus 30 degrees, right? Because sine of 30 degrees is pretty simple to find, right? So 210, we have already passed apoapsis. So this is something that's like that. This is an educated guess, right? What time is it? Already passed the core. Do you want to stop here and do the next in the next lecture, or do you want to continue? Okay, so let's stop here. We are going to pick back up here. We're going to solve this example, and then we are going to start the interplanetary flights. And see you all on Thursday. And I told Lawson I'm taking my second dose of the vaccine today. Hopefully, I won't feel anything. But if I was uncomfortable or whatever, we may need to cancel the class on Thursday. But I will make sure to upload a lecture for you. Okay. Have a good day.